All right, hey, I wanted to show you guys how some of the more professional modern software works with image files from CCD cameras, particularly when it comes to dealing with bias frames, flat fields, and dark frames, and total image calibration. This is kind of mind-blowingly cool because it works so well when you're dealing with professional software. This is what we have in our lab here at school, but you're not going to have this available to you at home. First, I'm going to open an image file. This particular image file is of an object called 3C273, which is a quasar. This thing's about 2.4 billion light years away, and if I zoom out, I can show you that it's this little white dot right there. And you know, it's funny that we think quasar, we tend to think supermassive black hole, accretion of matter into the black hole, hitting the magnetic field lines and being ejected in these jets, and it's super luminous and all that. But in reality, what you see, because the thing is 2.4 billion light years away, is a dot of light at about a magnitude 12.4, 12.5. Definitely not visible to the human eye, but it is visible in a small telescope like an 8-inch diameter telescope. This image was taken with our new 0.7 meter telescope, and you can see it has the telltale signs of having a brighter center and a darker edge, and it's got some speckly stuff in there, which is actually dark noise right here. This signal here that you see that looks like white speckles, that's actually from the thermal signal from the chip, which is heat buildup. This, by the way, was taken at a temperature of negative 30 Celsius. So, yeah, dark noise is real. This is a 5-minute exposure through a luminance filter. That means a filter that's basically a sheet of clear glass. There are no wavelength bands being blocked here. Now, the cool thing is calibration. I kind of didn't tell you the whole truth about image calibration. There is a reality here that it's not just one bias frame, and it's not just one dark frame, and it's not just one flat field that you're dealing with. Astronomers have discovered that the qualities of darks, flats, and biases, things really do get improved if you take a whole bunch of them. So take 30 or so dark frames, and take like 50 or even 60 flat fields per filter, and take another 20 or 30 bias frames. And for each one of those groups, you average them together to make a master bias, a master dark, and a master flat field. So that's what the software does, which is really cool. So if I go to the process menu and then choose select calibration, I can actually tell it to go to a specific folder. In this case, it's my desktop process 0.7 meter N30 for negative 30. The word process here signals to me that these are my files that I'm using to calibrate or process the image. And then I tell it to auto-generate a list of the process frames, and it goes and it reads that directory, and it literally builds a list of all the frames that are in there. So let's look at this a little bit more carefully. The very first couple are flat fields for B, for blue, and red, RC, then V, which is green. And each one of those is a full frame of 4096 square, taken at a temperature of negative 30 degrees Celsius, and there are 5 of each. And then there are 5 bias frames taken at negative 30, and then there are 5 dark frames taken for 5 minutes each, and then there are flats for the rest of them, hydrogen alpha and the luminance, which is going to be automatically used here, oxygen 3 and sulfur 2 narrowband filters. Now I just say OK, and now it has that in its memory and now knows where to go to get the appropriate flats, darks, and biases to deal with this luminance image of 3C273. So watch this. This is pretty cool. The software just does it all behind the scenes. Ready? I select process, then calibrate. and then off it goes, and it calibrates the image. And the output is pretty remarkable, actually. You'll see it change pretty dramatically. So there it is. The image has been calibrated. Look how nice and even and smooth that is. All those speckles are gone. In fact, it's pretty telling that it's a nice clean field. Notice also that I'm only looking at it 25%. If we zoom in to 100%, now you can really see just how smooth this field is. It's pretty remarkable. So here's our quasar right there. And here are a couple of nearby stars that are in our galaxy. All of these objects are nearby stars. And if we zoom in considerably, you can start getting to the pixel level. So we'll zoom in a lot. Let's just look at any object. Let's look at any object. I don't care what it is. We'll just zoom in a lot. So now you can see individual pixels of this object here. Now, even more cool is in this software, we can look at a graph window and select area plot and draw a box around the object of interest, and you can now see a three-dimensional representation of this CCD image. And the y-axis vertically is the pixel values between 0 and 65,535, 0 being black, 65,535 being pure white. This object is peaking someplace around the 22,000 level. So yeah, we're getting there. It's about a third of the way to full well, or full well capacity. But also of interest here is if you take a look at the bottom, it doesn't quite hit 0. It's above 2,000-ish. So I tell you what, let's draw another box that just looks at the dark background. So there we go, the dark background. This is sky. This is what the sky background looks like, and you can tell it's pretty noisy, but it doesn't hit 0. It's always somewhere around 2480, peaking somewhere just about 2560, 2570 or so for some of the brighter individual pixels. And when we look at it, there are indeed some higher energy pixels than others. And this is actually a measure of the sky glow. The sky above our heads is never exactly completely dark, but we have removed dark frames, dealt with the bias signal and the randomness of that. And we've averaged all those together to do our best job of minimizing the amount of noise and unwanted signal that happens to be in this particular image. So it's pretty cool. When software does it automatically, it's a really good thing. Unfortunately, freeware software doesn't do this so easily, as you will see in upcoming lab activity. Sorry about that. I know it's going to be a little bit challenging, but there you go. Okay, so enough of this. I will let you get back to whatever else you were doing, but I figured it was important to show you how real flats, darks, and biases are dealt with on a grander, larger scale.